Yeah, now it is. Okay. So very pleased to have Roman Kotecky to give us a talk on abstract framework for non-perturbative renormalisation.
Okay, so as I started to say, the only reason for this talk is that somehow that this is based on a very old paper, this one that we wrote with David Price in '79. Okay, it was dedicated to my supervisor Václav Votruba on the occasion of his 70th birthday. David. Mm-hmm. And
you will make it available?
Pardon?
Can you
I
make it?
can make it available. Okay.
Which journal?
And somehow this is Czechoslovak Journal of Physics B. Yeah. So it's So as a result, so first of all, I would like to say three things. So we had some vision. What is renormalization? And recently I read somewhere, and I'm unable to find the citation, but somewhere in New York Review of Books, I read somewhere somebody was saying, if you have a vision, you should go to eye doctor. Maybe we should have taken this advice. So we had this vision that we somehow understand what renormalization in non-perturbative sense should be, but it never realized because we somehow never pursued it after that, and so we only somehow suggested the thing in this obscure journal. So it was cited only once, this paper, namely in this paper by Vershi last year.
But that's important.
Yeah, okay, but only after, after I heard his talk. I was in Yerevan on a workshop 2 years ago, and he was giving this talk about, these filtrations of things. And in one part, somehow what he was showing, I was saying, we were exactly doing this with David in this paper. So he asked me for the paper, and he somehow liked it, and he put it into, so he's quoting this paper. So this is the only citation this paper had. Okay. So let me now start to use this feature here. So all is based on the notion of the projective limit. So let me somehow first introduce this. Projective. People nowadays also say inverse. Inverse limit. Okay. So what it is, let me show it on an example of, it's a general category theory concept, this projective limit, but in a lot of subjects, very easy use is for topological spaces. So let me introduce it for topological spaces. So for me, I will talk about topological spaces, and there will be morphisms between them, and morphisms for topological spaces will be just continuous mappings. Yeah? So these are topological spaces, and these are continuous maps. Okay? And now we have a directed poset, directed partially ordered set. Of indices. Okay, think about, for example, when we are talking about Gibbs states, we have sequence of volumes. Okay? So these are just my indices, satisfying, these poset axioms that if you have alpha, beta, gamma, so let me derive it. Alpha, beta, gamma. So if alpha is smaller than beta and gamma is bigger than beta, and beta is smaller than gamma, then alpha is smaller than gamma. This is one of the axioms. Another axiom is that whenever you have alpha and beta elements, there exists gamma here somehow that is bigger than those two.
So directed, it is what directed then?
It is directed, so this is this
Ah,
somehow.
okay.
Okay, you choose one direction somehow. Okay. So I have this. Now I will introduce something what we call projective, or what is this called, projective system. Nowadays, this is more notion from the other group of people. This is what they are writing on their boards, and probably they are using this inverse limit, because nowadays I saw when I searched in Google, I saw less of this projective, but I'm sort of accustomed to this projective limit. So let me use this nomenclature. So projective system is simply collection of spaces labeled by my indices. Okay, so it is, you say generalized sequence of topological spaces with the morphisms between them. So whenever you have, alpha, beta, such that alpha is smaller than beta is smaller than gamma, so let me have it like that. So you have a morphism, phi, alpha, beta between them, and another morphism, phi, beta, gamma between them, and they satisfy this diagram that if you have this morphism, then this morphism, then you have morphism, alpha, gamma, that is closing this diagram. Okay, so this is projective system. You have this generalized sequence labeled by alpha, betas, gammas, and so on. You have this sequence here, and you have a lot of morphisms between them. Whenever two alpha and beta are somehow ordered in this sense, there is an arrow between them, then you have a morphism between the corresponding spaces. Okay? So, and now projective limit is the following thing. Projective limit. So you have your collections, X alpha, let me just put two of them, with those arrows, phi alpha beta between them. Okay? And our projective limit is a topological space X with morphisms that are called projections going to corresponding spaces X alpha. So the projective limit is the pair X and the collections of these pi alphas. Okay, such that whenever you have Y, and also okay, and it is compatible. It is compatible with the sense. It is indicated on this picture that you have this commutativity here, that pi alpha equals pi alpha beta pi beta. If you go this way or that way, you are getting the same thing. So this is compatibility. Okay. So projective limit is such a pair where you have a topological space and you have these projections that are compatible in this sense. Compatible with your projective system, such that whenever you have another Y with compatible system like that, okay, so let me call these guys here phi beta and phi alpha, whenever I have a topological space and morphisms and the sequence, or whenever I have something like X phi alpha, Y phi alpha, whenever I have such collections, that is again compatible, which I indicate by drawing in this graph here, okay? Then there exists a unique morphism phi from Y to X that will close it in a commutative manner. Okay, so there exists unique phi from Y to X such that phi beta equals, first I go with phi to x and then with phi beta to x alpha. Okay? Oh, I wrote beta. So for every beta. Okay? So is this clear? And somehow to prove, so for topological spaces, what's happening? It has some glitches in the system. Okay, so what we see here, for topological spaces, it is easy to prove that such a projective limit exists. And actually, what it will be, it can be identified with sequences of elements from these spaces, so you can somehow, so your space X will be collections of elements X that are actually sequences of X alpha, okay, that are compatible in the sense that for every alpha and beta such that alpha is smaller than beta, then X alpha equals phi alpha beta X theta. Okay, so you have sequences of compatible elements, okay, and this will be your space X. Okay, you will make it into topological space and things like that. Okay, and clearly this will be somehow, this will, or it's easy to show that it will satisfy the axioms, and it can be easily proved that X is unique. In the following sense, that whenever you have Y that has the same property, then it's homeomorphic with X.
You do it both ways.
Yeah, it's biject. There is a homeomorphism, bijective homeomorphism. Okay. So this was the world of topology, where it was easy to introduce the thing. Now let me use this feature again, and we can go to probability. Okay. So let me just cover it for a second. Get my computer. Okay.
So, sorry, in the definition of projective limit,
Yeah.
no? I mean, given it always exists, it's not.
For topological spaces, it always exists. Yeah. Now I
So,
can.
sorry, but then, okay, no, I didn't follow the requirement. So the requirement is that whenever you have, you have this projection, and whenever you have
this part
another
of
space,
projection, and whenever you have Y, there are some
there should be phi.
there should be phi,
Okay.
so that actually this phi can be made. So in some sense, X is minimal.
Yeah, sure.
Yeah.
But it's actually pretty hard to see a case where it wouldn't exist, even if they aren't topological spaces. For example, the continuity of phi is.
Well, for the measurable spaces as we are going to, I want to. Where is my
Push it
You
lower.
have to go
Go a little bit lower.
with both of them?
with both of them.
Yeah.
More,
The 10.2.
and then magic.
Okay. Okay. So there is an old history to make this into, make sense of this for measure spaces. There are, it starts with Bochner in 55, and then there was Hoxie in 58, Dinsualeanu in 69, and for us the main two sources around the time we were writing our paper was this, this paper by Zdeněk Frolik. This is from, this was at this conference. Okay, so this is this Berkeley symposium. So this was 6th Berkeley symposium. It's published in 72, but symposium was in 70. Okay, So this explains why it's possible that Frolic was there, because 70 was still, after 68 we had this 1-2 years of somehow remaining freedom, and then they closed the boundary and then it was over. So we were all somehow admiring that time, this was somebody who was in America. Berkeley. So, and the other paper was Rao, and this is from, it's not written here, but I believe it's from 71 or 72, something like that. 70, okay. Strangely enough, he's not quoting Frolic's paper. And both this, and then Rao put it into his book, so it is somehow part of his book. Already here he is quoting, more details in the book. And they somehow incorporated all the preceding results by, Bochner, Hoxie, and Dean Suleanu. So these are the papers where somehow the notion of projective limit of measure spaces. Okay. So again, I can get rid of this. I was actually in Mathematical Institute of Academy of Sciences, and Frolic was my head of department. So, and I was there because I was interested in Feynman path integrals, and he had something that was called uniform measures, I believe, some very general notion of measures, and he believed that Feynman path integrals can be incorporated into that, which was proven. It's not possible. There were these papers by Cameron that essentially you cannot make sense of Feynman path integrals.
You can, but they are not measured.
No, there cannot be anything that is, signed measure or complex measure, has the property of measure, and is, and corresponds to whatever you want. Yeah. Okay. So let me look on this in the case of measurable spaces. So we have, our object will be measurable spaces. Okay. And somehow in our paper we needed assumption that with points in it, so if you have in F, okay, so whenever you have X in X, then the set containing just this X. Okay, so this is the only thing we have here. Then we have a set of measures. Okay, so Mx is a linear space. So let me write it down. Linear space of sigma-additive measures. Maybe we wanted finite. Yes, we wanted finite measures. Okay, and then Bx is the set of measurable bounded functions. This is just bounded functions. At one moment I will need topology, so this is how we define. And morphisms, okay, here, so morphisms phi, this will be not mapping from X to Y, but it will be mappings from Mx to My. So morphisms, we say morphism from X to Y, but what we mean it's from this set of measures Mx into set of measure My with the following properties. It will have two properties. So the first is that it is linear, non-negative, if you have positive measure, then it maps it again into positive measure, and it will be contractive. So it means that phi of mu, this is a measure with which you measure y. These are finite measures, so it's smaller or equal than x. And the second condition is exactly that phi is continuous with respect to weak topologies. Weak topologies on this mx that are given by measurable bounded functions. Okay?
So we don't suppose the total mass to have any sign. I mean, can
No.
have a sign.
Because it's linear space, so I need to, so it's in this sense. But it's non-negative, so it is somehow, it keeps this positivity in this sense. But you can think about probabilities as a subset of this, but then the probabilities are not linear space. Yeah? And I want linear space. Okay. As you will see, it is somehow, it is all this, I should say it first, somehow all this is in some sense extension of Kolmogorov's theorem, but in, there is this compatibility, so compatibility is something you have in Kolmogorov's theorem, but somehow alternative sense, so to say. It's an alternative to Kolmogorov in some sense, okay? And it is using the fact that somehow you are working with measures and not, and not one measure, but a space of measures somehow. And this will be important for us when we return to field theory. Okay? And then this projective limit, everything, you have the arrows, so everything will be the same. Okay, so x, phi alpha, p alpha will be projective limit in this sense. Okay? It's by the way, this projective limit you write like that. Projective limit of the collection x alpha, phi alpha, beta.
So these p alpha state projections,
Pardon?
p alpha.
P alpha
They are continuous mappings, so you need
Yeah,
topology.
continues in this weak topology.
Okay.
Okay? So there is one somehow special feature of this, and this is somehow that has to do with Kolmogorov.
Yeah, here you have a problem in notation. No? X is not X, is M of something.
Yeah, but somehow I am somehow. This is a mapping from mx to y, but I am saying that this is a morphism from x to y. Yeah. So morphism is a mapping from mx to y. Yeah. Morphism is not necessarily, somehow this is in this category language. You can declare the objects to be whatever you want and morphisms to be whatever you want. So here I do it in this sense. Okay. So by the way, here is the following property. Whenever I have mu.
So, sorry, in the notation, pi alpha, what exactly is this? The pi alpha is just all of these little mappings that I see. All right.
Yeah. But they are in the sense of measures here somehow. So if I have a measure mu, I have pi alpha of mu, okay, which belongs to mx alpha. Okay. And they are automatically compatible, so this is a compatible sequence of measures. Okay. If you apply this phi alpha beta on them, you are getting exactly pi beta of mu. Okay. So whenever you have mu here measured on x, then you have automatically compatible sequence of measures. Okay. And it's actually bijection. So whenever you have a compatible sequence of measures, and this is somehow essentially the Kolmogorov side of the claim, whenever you have compatible sequence of measures, mu alpha, and it's compatible, so somehow mu alpha equals phi alpha beta mu beta. Okay, so you have compatible sequence in this sense. There exists a measure on this x of which these mu alphas are projections, so to say. But projection is not literally projection. Projection is simply some mapping.
So yeah, logically, because otherwise I got lost. I mean, so you do this first, so you have this compatible family, so you construct the measure.
Yeah. Okay, I should also say that somehow here the existence of the measure is not trivial. It's not always automatically somehow, and you need some conditions which are somehow formulated in Borcher's. So there are these Borcher's conditions, and whenever Borcher's conditions are satisfied, you have existence of the thing. So I will, and all this, there are these two papers I was citing, this Rao and Frolik, so they somehow have all possibility of
so you
generalization.
use the result to say
Yeah,
that
yeah,
this
yeah,
limit
yeah.
exists.
Yeah,
Okay.
exactly. And actually, once I know that the limit exists, I can prove here that if I have this sequence, so having any mu on X, I have a sequence of compatible guys. Okay? Whenever I have a sequence of pi alpha mu, yeah? Whenever I have sequence of compatible guys, there exists necessarily a measure here that is pre-image of this mu alphas. Okay? So there exists such mu, and why it is true? It is true by this. You can take, any y, so take any non-empty y. Okay, I will do something very trivial, and put R alpha, or how I call them, phi alpha. So phi alpha will be the map that any measure rho on y, this is measure on rho, it will map into rho of y times this mu alpha. I have a sequence of mu alphas. Okay, so I have a non-empty measure space, and on this space, so for example containing just one point, and on this space I will consider a measure, and I will define these mappings phi alpha such that they are giving me there is a fixed sequence mu alphas that is compatible, so they will give me mu alpha multiplied by some number, rho of y. Okay? And then by this is, you have this phi alpha, phi beta, and they clearly give you somehow commutative diagram here. So by this there exists this phi, that is sending the rho into mu. Okay. And this mu will be our pre-image of this one. Okay.
So this, the condition in the Kolmogorov theorem that you'd be considering measures on compact space, that is the Borcher's. That's what Borcher's does.
Yeah, because it's generalized. Somehow nobody is interested in compact space. They are interested in non-Hausdorff topological spaces, and you measure some of that, or something like that. So these are very general things. The conditions they have. Yeah. Of course, we are going to use it in simple situations. Just.
What was the point of this argument?
The argument was that whenever I have a sequence of compatible measures, then there exists a unique mu such that this sequence is projection of this mu. So essentially I'm proving existence of the limit in Kolmogorov sense. I have compatible somehow think about them as finite dimensional projections, okay? So I have this sequence of projections that are somehow compatible. Then there must exist a limiting measure such that they are somehow projections, they are marginal, so okay? Okay. So let me now illustrate this part. You will remember this graph, so I can somehow get rid of them. Yeah? Let me just look on the Gibbs states from this point of view. And there it works very nicely, everything. So we have Gibbs measures. And we are citing a paper there, paper number 1 in our paper, and this is our paper where the details are done in full detail somehow, okay? Which I totally forgot we were thinking about writing something like that. When I was somehow inspecting this paper, so somehow, because for Gibbs measure, so it's somehow clear we wanted just to put all the details, and somehow this is a nice way of formulating DLR equations and all that. So we wanted to write it down, but our main idea was to go to field theory, to quantum field theory, and we somehow didn't quite succeed to do it. And then we started to be, this was 79, in 80, I was writing my paper with Senya about Potts models, and David was writing his, proving the conjecture from this famous conjecture by Federer. So somehow we were on different paths, and we had no time really to finish this. So probably it is somewhere in my papers, this paper one, somewhere in my, somewhere in some desk, in some forgotten desk. Okay, so let me think about Gibbs states. So I will not prove everything here, but somehow Gibbs measures. But let me just indicate, here everything is very clear. So we have just a space. Let me think about the simple case where I have product over X's, and I have S, the same, say, finite space, some spin space. X is the D. Okay, so this is my omega. Whenever I have a subset of the D lambda, I also have omega lambda, where I restrict this product over X's in lambda. And I have a measure, let me denote it like that. Nu lambda with boundary condition W is simply E2 minus beta H lambda. And now you have some U under the boundary condition W divided by the sum over V in omega lambda E2 minus beta H lambda E W. Okay, so this is the measure in finite volume with boundary condition W. Okay? And now, what is Gibbs measure? Mu is simply you take a sequence of these W's, and if you really want, somehow to get all, you can take this, you can take sequence of lambdas and sequence of W's, and you look on the limit, okay? But then you do not get all the Gibbs measures. You are getting only some extremal you can get in that way, but somehow you need to take convexification, and you need to take convexification and close set, and then you will have all Gibbs states, okay? All Gibbs states you get by DLR, but by the limits you are not getting all. So to get all, you have to take limit, you take the boundary conditions in sense of measures, okay? So I have a sequence of the volumes, lambda n, and of the measures, mu n, and mu n are measures on omega, on the complement, on omega lambda complement. Okay, outside. So these are measure boundary conditions. So I have this sequence, and then I have a limit. This I'm going to infinity of what? Of integral nu lambda n w restricted to lambda n complement. Okay. With outside I take the delta measure. So this is a measure on lambda n. I add the measure on outside, just the delta measure on complement on the outside, and this I integrate with this du n. Okay, and you do all possible limits, and you are getting all possible measures. Okay. So of course you can introduce this notion here, which is the specification. And so there is this is the probabilistic kernel called specification. Let me call it Q lambda and what we have, it is function, you know, here I have restriction to only complement of n, but it makes sense to define it for every w, it will be only measurable on outside somehow. So it is a function in w, and it is a measure in what? In u. Okay? And all this w and u are in the full space. Yeah? Because this u here will, on the outside of the boundary, will be to this w, and then I'm looking on this object. So this is the probabilistic kernel. Okay, so what is written here in terms of this kernel is somehow I am integrating this kernel over this w with this measure, and then I am taking element. Okay? And these kernels, they satisfy the somehow compatibility conditions. So for whenever you have subset of lambda, let me take the subset of lambda, then q lambda equals q lambda times qd. What I mean by that is, for example, I can formulate it like that q lambda in w applied to a function f, this is, here it is a measure, so I can apply it to some function, equals whatever I will get if I take q lambda with this boundary condition, but I apply it to a function which is qv dot applied to function f. Okay, this is a function in this variable, so I apply this measure on that, and I will get exactly this. Okay, so this is this, that I somehow take boundary condition w in lambda and apply this directly on the function. I apply this measure here directly on a function, or I first somehow apply smaller volume on the function, the Gibbs state in smaller volume, and then I apply this bigger volume. So there is this consistency. Okay, here it is, in this language of specification, everything is very clear. Okay? And of course, DLR then is simply saying that Gibbs state, if you have a Gibbs state mu, it satisfies the equation where what side it goes from mu to n. Okay? For every lambda. You take the measure and you take it as a boundary condition, you integrate, you take this thing here, you integrate over your Gibbs state with this boundary condition, you are getting the same Gibbs state. Okay. And the specific feature of this is that this sequence of measures we are getting here actually doesn't depend on lambda. Okay. So this is the thing that you have this DLR. Okay. So how we now say it in this language of projective limits? Okay, we have to introduce this this projective system. So I will have the spaces omega. So let me say V complement here, which is bigger. This is strange, which is bigger. I have this omega lambda complement here, okay, and I will have a map, yes, P, V, lambda, so this will be what I denoted phi alpha beta there, and this map is defined in the following way. I have a measure with boundary condition, so I take a measure on the boundary conditions outside of lambda, and I make it into measure outside on the boundary condition outside of V. Okay, so I have a measure mu lambda. Okay, and with this measure I compute this object over there. Integral mu lambda w on the complement times delta function on the lambda complement, and I integrate this with this measure mu this is a measure on lambda. Okay? And this measure, because I integrated out the, somehow out of the, it is actually the measure on the full space, but somehow outside it is this delta function. So it's a real measure, it is somehow on lambda. And what now I want to do is somehow to forget the part that is inside of V. Okay, so I take somehow the marginal onto complement of V.
What's the relation between V and lambda here?
V is subset. V is subset of lambda. Okay, so I had this mu lambda here. So I have lambda, I have V. So I have outside, I have this mu lambda, and I want to have mu V that will be somehow defined as a boundary condition for this. And here is the definition, this equals mu V. Yeah. I take this somehow Gibbs state in the volume lambda with the boundary condition mu lambda, and now I forget about the variables that are inside of V, and I am getting something that is living on the strip, on this strip between those two. Outside I keep W or this mu lambda, but here inside I have this margin. Okay, so this is mu V. Okay. And this is my map. And then the Gibbs state is simply projective. The set of Gibbs states is projective limit of this system. Yeah. And it is somehow, the important thing here is, it is not Taylor sigma algebra. It depends on temperature, it depends on everything. These mappings here, they depend on this. So they depend on temperature and Hamiltonian and where you are in your phase diagram. So actually your projective limit will be effectively just in the places you have only one Gibbs state, it will be 1 point state, and the places where you have two Gibbs states, it will be this interval. Yeah, it will be measured 2 point states of some delta function on pluses and delta function of minuses, and linear combinations of those. Okay, so somehow it is the projective limit is not just saying that you have so it's really describing the set of all Gibbs states. Okay, so it's very convenient. Okay, but my main thing was to say something about quantum field theory. So let me, okay, so quantum field theory. So let me go to quantum field theory. And of course, let me talk about phi for whatever, phi for d. So we would like to understand what is renormalization without really going into any perturbation theory? Whether it's possible to use this machinery to at least define what is renormalizable and what is non-renormalizable. Okay, so we have this, I even do not need to write it down. So I have, I'm interested in phi d4. Okay, so it is clear what I want to construct. Okay, so if I look on the, somehow imagine that I will somehow I will take a finite volume L, and I will take a lattice approximation. So I have this where this is some of delta. Okay, so I will have functions that are step functions. So this will be my space. So my space, let me call it y alpha here. Okay, so y alpha, I have a space y, so let me write it like that. I have a space y, which is where my measure will be living. So it is, somehow S prime of R. Okay, this is my aim, to construct a measure living on S prime of R. Okay, now I take finite approximations of this space. Okay, so this will be finite dimensional spaces that are spaces of step function with the size delta here, and living in the volume given by L here. Okay, so collectively this delta and L I denote as alpha. Okay, so I have this spaces, finite dimensional spaces Y alpha. Okay. And of course I can choose, this L to be double or things like that, and this delta to be half, so I have somehow clear subdivision, which is a subspace of which. Okay. And I have some morphism for every of these spaces. I have some morphism T alpha that goes from Y alpha to Y. Okay. So actually I will somehow reformulate it, not speaking about, the sequence of spaces and these morphisms between them, but I will talk about that, but what I have in mind is somehow to embed everything into my Y, into S prime. So I'm thinking about, somehow being as a different approximation inside of S prime. Okay? And what will be my measure? So let me introduce now for every alpha, I will have this measure mu alpha, and it will depend on 3 parameters, Z, M, and lambda. Okay, and this will be, of course, the standard thing. I will have E2 minus sum over nearest neighbors X and Y. Okay, I did like that. Z times, and from no reason I write here delta to D minus 2, phi x minus phi y squared, and then I have, I put it into parentheses like that. Okay, so I write plus here, plus m times sum delta to the D phi x squared plus sum delta to the D times lambda phi x to the 4th power. Okay? This is just example. You can of course do it for any somehow for any field theory divided by some sort of renormalization. Okay? Of course you have product over axis. Okay, so this is this is a measure on this space, on Y alpha space. Okay. And what is our aim now is to look on the all possible limits. So this would be somehow in the standard language. What you guys are looking at is somehow to look on the all possible limits where you take sequence of alphas and where you take this Z. You somehow choose some sequence Z alpha, M alpha, and lambda alpha. And you go to the limit when alpha goes to infinity. Okay? So this would be the task to find all possible limits. Go through all possible sequences, find all possible limits. Okay? This is what you are doing, but you are doing it in somehow restrictive way because you choose your Z alpha, M alpha, lambda alpha. By input you have from perturbation theory, so you know what Z alpha, M alpha, and lambda alpha will work, what counter terms you have to choose, and things like that. Yeah? But I would like to put it as a framework, so I would like to understand what I can do. So imagine I take all possible limits with all possible sequences. So what's all possible sequences like that? Sometimes the limit doesn't exist, but if it exists, it might be something. In a lot of spaces will be something trivial, some Gaussian measure, or some delta function or something like that, but in some cases it might be something interesting. I take the set of all possible limits.
In the set of measures on S prime?
Yeah.
Yeah.
Yeah. And I would like to understand what it is. Okay? And now I will say that the theory is renormalizable if the space of the limits is not big.
And you require limit as opposed to subsequence?
Yes, because these are all possible limits, so I can choose a subsequence. This is part of it. If it doesn't exist, then I do not care. Yeah, so it's all possible limits. I take all possible sequences. I take all possible limits. Okay. So somehow it is a bold statement, but we were encouraged by a stupid example. There was something, you know, and now somehow you might remember there was Clowder had a sequence of papers where he introduced a stupid thing which is called ultra-local field theory.
Still has this.
Pardon?
It still has.
It still exists?
Yeah, I mean,
Ultra-local
it-
field
it
theory
is
is
book
when
in
you
the last
forget
chapter.
where it is, it's here. When you forget the gradient term, when you simply do not take kinetic energy.
Actually, he's claiming that this is the way to solve phi 4.
And he is claiming, so he's still alive, Clowder, or?
I don't know, but I read a book which is written recently, and in
Because
the last
we-
chapter it discusses.
I remember, you know, somehow there is this crazy story. Oh, it's okay, recording. so we had this, there was this winter school in Karpacz. I was never moving outside of the Soviet bloc. So there was this winter school in Karpacz, and we were there, and with Krzysztof Gałęzki every evening we were playing poker and drinking and something. And then Clowder arrived. And, you know, with David, when we were somehow writing papers I will show you now, we somehow called this paper Hammer on Clowder. Yeah, because, you know, Clowder is nonsense, and we wanted to show that it is a nonsense. And we have these two papers where we clearly prove that it is a nonsense somehow. What he was claiming is nonsense. So we called it Hammer on Clowder, and we were somehow sitting in Michael Bridge, and we were somehow working crazily on that. And then there was this winter school, and Clowder arrived there. And while we were with Krzysztof drinking this, you know, whatever we had, we finished our drinking, and we were still playing poker at 2 in the morning. He arrived, Clowder, by some, you know, lane. It's difficult to arrive to this Karpacz. He arrived, and, you know, I never met him before, but I said, okay, you are here. Do you have something to drink? We finished our drink, and he somehow came with this, you know, precious, you know, some sort of Cointreau or something horrible. So we were drinking, we drank half of the bottle of this Cointreau. Then he came and took it from us. He said, I actually brought it to Opushansky, so, so it was already half empty. And then my wife arrived for the weekend, and so she met this Clowder, and so when I introduced them, she said, oh, I know your name, I heard only horrible things about it. And she meant this, you know, Hammer on Clowder, so I wanted to smooth it somehow. So I said, you know, I told her the story when you have taken the bottle from her. so this was the thing. So the papers are here. So this is the paper from 77, I believe. Yeah, 77, from Letters of Mathematical Physics. It's actually volume 2, so it was one of the first issues of Letters of Mathematical Physics. And what we did, we took, you know, somehow you take this, you forget the gradient term, so you take exactly what Clowder was doing, and you consider all possible limits, and you can really solve it. You can somehow find the set of all possible limits. And it contains, he was somehow claiming that you cannot, I do not remember what he was exactly claiming, but that you cannot, that it is something non-perturbative, and you cannot go to you know, somehow by perturbative way, you cannot get result in this. But you know, you can get all possible results, including all possible delta functions on the boundary, but it's true that the set of limits, and we have another paper 1 year later in PhysFD, where we somehow, you know, this non-perturbative normalizer for a class of gradient-free models. So these are this ultra-local gradient-free, we simply do not put gradient there. And it's essentially trivial. You are able to find all possible limits, and there is finite dimensional set of them. So it is renormalizable, yeah, by my definition of renormalizability. Renormalizability means that the set of possible limits is finite dimensional. Yeah. Whatever it means. Yeah. So this is renormalizability. I will take all possible limits.
I mean, you cannot, what do you mean finite dimensional? It's a finite set, or it's?
No, it's finite dimensional set, so it can be mapped into a subset of Rd, of Rn. Whatever.
dimensional.
It's manifold in finite
Yeah.
dimensional space with finitely many dimensions. It has finitely many dimensions in some sense. It's
No,
Yeah.
sorry,
Yeah.
it was.
yeah. Okay. And in this ultra-local play situation, we were able really to compute all limits, and it was finite dimensional space. Okay. And it's because why it is renormalizable? Because then you can fix a measure by finitely many parameters, by some physical measurements. You measure real mass because this is what is here is bare mass and this is bare interaction or whatever, but you have a real physical mass that you measure in experiment. You have real physical interaction. You measure some scattering. You have some cross section, and you somehow measure this cross section. So you have these physical parameters, and by finitely many physical parameters, you choose your theory, your limit. And then you have a predictive power. Then you can, anything else what this, measure is containing in it, all possible other, somehow moments or whatever, you can compute them, and you have some predictions. While if this space is infinitely dimensional, then you cannot say anything, and you cannot use it to predict something. You have to choose out of this infinitely dimensional space. You have to choose one measure and say this is from some different reason, not from the reasons having finitely many physical parameters that is choosing that. And it is somehow indicated, of course, by perturbative field theory, because what is non-renormalizable theory? 4 in the dimension 5, for example, is non-renormalizable because in every higher order, if you add higher order terms in your perturbation, you need counter terms that were not before there. So you need to add higher power of your phi or something like that. Am I right?
Well,
David?
I'm a bit confused because if I started off with in higher dimensions with a phi to the 4th term, I would just simply lose it, and I would end up with only delta functions and Gaussians.
You will, but this you...
So it's renormalizable in your sense.
No, it is in my sense it's renormalizable, but in perturbative sense it's non-renormalizable.
That's right.
In perturbative sense you are getting these mu and nu counter terms, and you cannot say phi 4 because you will have phi 6 also.
Right.
Yeah.
But yes.
And phi 8 in higher order and things like that. So you will have counter terms to higher and higher order, it never closes. Yeah. So here it will, I agree, I mean in our sense it is renormalizable even in trivial manner.
Yeah,
There
not
are
so
only
clear
trivial
because,
solutions.
of course, you don't have to be guided by perturbation theory. You could take a phi to the
I agree.
phi to the 4th
I agree.
in more than 5 dimensions, and maybe you would find a finite
Yeah, yeah.
dimensional.
Sure,
Which
sure.
doesn't include
Sure.
one of these things.
But nobody is doing that.
Right.
Everybody is somehow relying on perturbative theory to find their counter terms, including
Well,
Martin.
of course,
for
there are
example, he takes
hypotheses
it
in these no-go theorems that say that you use limits where Z is positive in that formula there. But then you get a theorem that there are.
Yeah. So let me finish that. Somehow I'm over time, but somehow do you agree? I have 5 minutes to finish that.
I don't know if you're over time because you have till 12:30.
Oh, very good. So then I can even somehow start a new bar. Because I would like to explain that I still didn't come to the main proposal, what we suggest to be done, and I still do not understand why we somehow didn't write it in more details, because it seems to me it's somehow working. I was recently talking with David about that, and he, to my surprise, he somehow remembered it. Because, for example, our cluster expansion, he didn't remember. He was saying, okay, I know there is such paper we wrote, and it is my most highly cited paper, but I do not remember what we did there. But for this, he remembered the details, what was the clue somehow. So already this suggests that it is something that is worth to. Okay. So how it is, there is one additional thing that I'm somehow doing here. Let me write it here maybe. Namely, I have this space y alpha, I have this space y, and I have this immersion T alpha. So I can somehow, so whenever I will have so by y alpha here, I will consider y alpha is the set of triplets Zm lambda, which is simply some subset of R3. Yeah, I do not allow all of them M should be positive or whatever. So somehow, so there are some set of triplets. This will be y alpha. This is how I am somehow labeling my measure here. And now the morphisms are somehow living on my alpha, and my alpha will be those measures here. Okay, not really. My alpha will be, so what will be the measure?
Sorry, I thought you would also take the cutoffs into the projective system.
Yeah.
You would have a lambda or something in addition.
No, this is in alpha. All is in alpha. Alpha contains delta and L.
So his lambda is his cutoff is the delta, so he has a...
Oh,
Yeah.
it's a,
Yeah.
it's all,
Yeah,
okay.
this is the alpha.
Yeah, it's
Alpha
a
contains
finite-
all possible whatever you
some
want.
finite
The
dimension.
ultraviolet, delta, and infrared lambda is there somehow. Yeah,
So
all
that is
cutoffs.
incorporated.
Yeah.
in the
So this is my alpha. So I have 3 parameters here, and I can consider measures on this space. This is my y alpha.
Okay.
I consider measures on this space.
Mhm.
Okay. And whenever I have such a measure, I have this mapping T alpha mu. So mu belongs to M y alpha. Okay. And T alpha mu, now I immerse this into my S prime. Yeah. And this T alpha mu is what? Is simply this integral mu alpha Zm lambda, which is written, this measure is written there, and I integrate it with my mu, d mu Zm lambda. Okay, I have some measure on the parameter Zm lambda, and I'm taking this. So this will be my, somehow, these are the measures with which I'm working, and I should define my my morphisms on them, my phi alpha beta morphisms. Okay. Okay. This is actually, this is the unique morphism extending because it's on linear space of the measures, but these are the measures somehow that are linear combinations of those, so to say. Okay. So this is a unique morphism. This guy is unique morphism extending Zm lambda, extending this map Zm lambda into mu alpha Zm lambda. Okay. S immersed in, on Y. On means let me write explicitly S prime. I think about this measure as a measure on S prime ID, and for any Zm lambda I have a measure for a now linear combination of Zm lambda represented by this measure. I have this thing here. Okay. So what are these somehow? So maybe I should say that I did some similar thing in the Gibbs. So maybe just in few sentences about Gibbs situation. In Gibbs situation, I also had this mapping T because I could think about these measures. Well, I just arose it, but there were these measures. This integral of nu times delta d mu. Okay, there were those measures. So I can think about them as measures on the full space. I can consider this to be a measure on a somehow T alpha is somehow taking this and putting it into as a measure to omega. Okay, and then you are working only on omega somehow. So you have the same space, you have only the mappings. Okay, so you have this, and then what were the mappings in this sense? What were the mappings of, what were the mappings? So I have these spaces Y alpha, which were in this case, it was this omega lambda complement. Okay, so these are my spaces Y alpha, and I have this phi alpha beta that were somehow that are given by this, how I denote it, PV lambda. These were this PV lambda, but I raised them to act on omega somehow. Yeah. So I can think about those, this PV lambda somehow. Okay. And then I have the projective limit of this somehow automatically. Okay, maybe I do not raise them. I stay in my original setting. Okay, so this is the first thing. So first thing, I have this phi alpha beta, and I have this, which is this, which is this PV lambda. Okay, and I have this projective system, and as a result, I have projective limit. So I am just, interpreting what I have there, x by okay, which means in this, I have this x and phi alpha in this. I want to write these letters because this I will use in a second for the field theory. Okay, and then if I look, so the following thing I have here is if I look on the sequence T alpha of phi alpha mu, okay, which is, I take these measures here, okay, and I interpret them as measures on omega, okay, so then automatically this is a consistent system of measures and automatically I'm getting a limit, okay, so this converges. Once mu is a probability on X. Yeah. So I have probability measure on X, and this creates, and this X is something small. This will be the space of, somehow will be just these two, one-dimensional or two-dimensional in situations where I have phase coexistence or not. Yeah. So I have this projective limit, and now I take a measure on this projection. So I take something that is representing mu plus mu lambda times mu plus 1 minus lambda times mu minus, for example. Okay. I take this.
I got confused here.
Okay. Yeah. So I'm saying it's in somehow.
So first, are you actually extending all of these measures, nu alpha, zm?
I should say I am extending them a posteriori. Now let me first stay with the standard, with the setting as it was before. Yeah. So I have this PV lambda, okay, which were this, which were living on the somehow on this were mapping of the mu. This is mapping of mu lambda into mu b.
Yes.
Okay, boundary conditions. But now I have a projective limit. And projective limit is something very small. In our case, it is just 1 point if I am outside of phase transition, and it is 2 points if I am on phase transition. Yeah? Because the set, it's describing the set of Gibbs measures, and there are, either 1 Gibbs measure or there are 2 Gibbs measures, 2 extremal Gibbs measures, and there are combinations.
So I'm still confused by the fact that you take.
So this X is something that depends on temperature and Hamiltonian and everything, and it is, you know, just this. It is just, it depends on what temperature, what external field you take. You are either on the phase transition or outside. If you are outside of phase transition, you have just one element here, so it is just 1 point.
And do you see that in the theory, or is this outside information you feed in?
This is, you know, somehow it must be like that because I was describing, this is the minimal set that is describing all Gibbs state. And I know that there is only one Gibbs state.
Okay, but why you have only two within the phase transition? You have all combinations as possible.
Yeah, exactly. But this is somehow, there will be this,
So you mean the
so
extreme?
there will be
you
the
have all
points.
extreme.
X will be 2 points.
Yeah.
And the measure on these are linear combinations of these 2 points.
Okay, so you have two
Yeah,
extremes.
so the measure on the set of 2 elements. But you know, it depends on this P, it depends on temperature. So sometimes I have 1 point, sometimes I have 2 points.
I think where I've gotten a little lost though is that we know that we have to vary these parameters, the alpha, beta, the z, mu, lambda as we take the limit. In what sense are these?
So
values
I am
compared-
still not in field theory. This is the,
Oh,
yeah.
okay.
I am talking now about, you know, about Gibbs states. Okay, so for Gibbs states it's like that. I have my projective limit, and now I can somehow look on this, you know, I have my mu, okay, and this mu is indeed only this, you know, measure on 2 points.
This mu is the projective limit, the mu?
Yeah, the mu is the measure on X.
Yeah.
And I have these projections, which are the maps that make this measure into the boundary condition measure. Yeah. And this boundary condition measure via this, I can somehow consider as a measure on omega. Yeah. And this sequence has a limit. Yeah. Why? Because it actually doesn't depend on alpha.
Yeah, that's
Yeah.
okay.
So the limit is already there. The limit is already there. Yeah. Once I took something that is representing Gibbs state, I am getting here something that doesn't depend on my thing. So I have a limit. Okay. So actually, and I can introduce the mapping T that goes from mx, so from my Gibbs states, into, so for any mu here, I'm getting, so let me write this up there. For any mu here, I'm getting a sequence T alpha, phi alpha mu, and this is the sequence of consistent of, so this mapping is a morphism.
You get all the sequence.
Yeah. Because this is somehow, you know, just raise this p lambda that is raised to the force somehow, to the measure on everything, okay? And then the third thing, somehow it's very vague, but somehow, you know, the set of Gibbs states is simply, what is a set of Gibbs states? It's a set of all mu, where mu belongs to mu x, to mx. Okay, so this is my description of the set of all Gibbs states. These are representatives of Gibbs states. These are really the Gibbs states. So this is how you use it. You use only the first step, you get projective limit, and this projective limit is something very tiny, it's just 1 point or 2 points in the case of Ising model, okay? And then you are somehow, you can raise it to give you the information about the set of all Gibbs
Would you say these Gibbs states, the set of Gibbs states are just a convex envelope of the...
Not even, these are, you know, mx.
Oh,
And what is mx? If you have 2 points, mx is lambda times 1 point plus 1 minus lambda times the second. Yeah, so that's why this mx is important, not to have a mapping on x, and also this condition that somehow x contains points the sigma algebra F contains points. This was somehow important for this. Okay, now let us come to field theory. And we would like to have something similar like that. So we would like to have, and it seems to us that the first 2 points you are somehow getting almost automatically. So we would like this. So we have this measure here. Let me maybe erase this. So we have this measure, okay? And now we need this, phi alpha beta. So I should also remember that my y alphas are just, somehow are just spaces of this, is the space of this and lambdas of these 2 plots. Similarly as, okay, so it is just something similarly as for Gibbs states, it was just the boundary conditions. Yeah. Okay. And now I need this mapping, phi alpha beta, that will be the mapping between measures on y beta into measures on y alpha. Okay. So it makes only sense if I somehow take this somehow, I will take some sequence alpha n plus 1 such that this one is refinement of the other one. Alpha n plus 1 is refinement of alpha n. Yeah. And now what we are proposing to take for phi alpha beta is simply, so we have this alpha, but we have the measures. These are measures of this type, actually linear combination of those over this. Okay. So I will define I will define it only for such pairs that are sort of one is refinement of the other. So I cut my delta into half and I make my volume twice as big. Okay. So this phi alpha n plus 1, okay, will be, I will take delta function of the space M y alpha n plus 1. Okay. So what I mean, I take simply this measure with a given parameters here. Okay. In the space alpha n plus 1. Okay. And what I will map it to, I will map it to some function mu in M y alpha n, okay, such that the distance of delta y and mu is minimum. Okay. So, okay, not exactly. Such that there somehow, if I take this one and put them into S prime, then their distance is minimum. Okay. So such that if I raise them, so this T alpha n as mu and T alpha n of delta y have minimal distance. Okay. So you have this, you have this refinement spaces, and you somehow define these guys by taking always when you start with delta function, when you start with delta function here, you take a linear combination of those, integral of those with over Zm and lambda, okay, on this smaller space that are the closest one to this delta function. Okay, you can interpret this delta function here as, you take both of them into your S prime, into your somehow overwhelming space. So you can think about this guy here as a measure here, this guy here as a measure here, but this guy here you take linear combinations of those measures with some measure mu over z m lambda. Okay, this is this guy here. Okay, and you take that one that is closest one. Okay. And then somehow it seems that the first two claims should be doable. And of course, what remains is the third thing, which is somehow to, you should be able to describe the projective limit, how big it is, whether it contains, this finite dimensional manifold, or whether it's bigger and things like that. So this is totally unclear to me. But somehow in analogy with this Gibbs state, the first two is somehow formulated here. And it seems to me that this idea, so there are two main ideas there. One idea is somehow to define this mapping as taking the closest guy somehow, and not to take the closest guy as another measure like that, but you allow linear combination. This was somehow important for Gibbs states, to allow the measures. You cannot take the boundary condition W in volume lambda and some other boundary condition WV in other volume in such a way that these two measures are closest ones. This wouldn't work. But if we took the consistent, because this is not possible to interpret as a Gibbs state on infinite volume. But if you have the measure outside and you have this consistent sequence, then it is exactly the Gibbs states on infinite volume. So this is the thing we will not have here. But I believe that something like that can be formulated. Yeah. So to show that in some reasonable, for example, in as you are saying in d-dimensional, if d is bigger than 4, you have. I should remind you that we wrote our paper 2 years before triviality of for d bigger than 4 was proven. So this should be somehow consequence of this limits that you are obtaining it that way. So somehow maybe you can forget about the projective limit and take only this part here. Somehow consider the sequence of measures, but you are then going this. The idea of projective limit is that you are somehow you have these mappings, but actually you are going in opposite directions.
They are consistent. I mean, they consistent. Because seem arbitrarily distinct to take minimal distance. No, it's not like something you already did. It's some heuristic.
Yeah. It is, consistency. I'm not, I was thinking about this, and it is not terribly clear. We are claiming that it is, but whether this is, somehow giving you the same, but it's giving you approximately the same. This I can imagine. You have triangular inequality, and somehow, and
So you need really a distance, so you look like Wasserstein or things like this.
Wasserstein with V, please, not with W.
I didn't write.
Yeah.
I don't know which distance do you have in mind, because I was
Yeah,
worried
somehow,
about
of course,
the way
David probably had in mind this, but this is essentially Wasserstein. There is this flat distance in Federer, or second half of Federer book is about these flat distances. Yeah, so flat distance is essentially something that's, in the simplest case, it's defined on the set of jets, and somehow, which I do not understand. But if you take the simplest case function, so you have indeed supremum over Lipschitz functions, and you apply this measure.
But I mean, you don't want not to resolve the very small scale, because I mean, usually what you do even in renormalization group is that you look at large scale. Then I can understand that you can approximate.
This is the opposite direction somehow. You have these steps. You are somehow looking on this maps.
Yeah, no, but the fact that this distance, no, I mean, if I look at the distance, which really resolve a very small scales, then I think I have trouble to approximate when I'm.
No, the distance must be defined here.
Yeah, that's
Yeah.
my point. I mean, the
That's
distance
his
could
word.
resolve a very small scales. So I cannot approximate a measure with another measure.
It will somehow, for some sequences of ends, it will not work. This somehow
It
contains
will-
renormalization.
Yeah, let me, there is no renormalization group here. There is no this idea that you look at large scales, no?
Because he's going in the opposite direction, I think.
No, the projective limit is bringing you somehow here. This x at the end is actually some limit going here in such a way that you try to be consistent all the way. But you have to choose your sequence, so you have to choose in Gibbs measures, you had to choose somehow the consistent sequence of the guys. So we believe that if you take consistent sequence of those guys that are somehow each smaller one is closest one to the biggest one, and you take them not in the sense of this measure, but on the measure on these parameters.
So let me try a consistency check. Now, if you don't let delta move, if you let move only L, does this give you back theory of Gibbs measure?
I have no boundary conditions. There is,
Yeah, but
zero boundary
yeah,
conditions.
but okay, but then in
Yeah.
this case, what does it give you? No, I mean, think about not fixing delta, so you're
Yeah,
not looking
yeah.
at the ultraviolet problem, just the infinite volume limit. What does this give?
It should work, isn't it so that it works for fixed ZM lambda? Yeah, it's just, I take a measure on, somehow.
Yeah, but they should give you phase transitions for that. Should give, I mean, the limiting object should be.
Well,
still
but this will be
stable.
in boundary conditions, so you should, somehow, we are mentioning actually that you could expand it by adding boundary conditions. Yeah, if you want to talk about phase transitions, then you should do that.
I didn't understood very well when you discussed it before even.
So if you,
I mean, you claim that there will be no limit, there will, I mean, what do you
no,
expect?
I think it works in that case because the infinite volume limit, so as you're given the infinite volume Gibbs measure, and then you look at the marginals of the infinite volume Gibbs measure as you progress from the right to the left in our terms, so this thing. They're all actually, each one of them is a linear combination of the measures that you construct on finite volume with different boundary conditions.
Yeah, that's okay, that's.
So I think it would work.
You take the points here, so
No,
this x in the Gibbs
Yeah,
equation,
if you ask.
this x
about
is
the-
just 2 points,
Yeah.
plus and minus, and you take those for boundary
No,
conditions.
Gibbs
and
I
then you have
understand,
somehow-
but in this case, what would be the projective limit?
I
Well,
think
If you don't put the boundary conditions,
So then I have 3 boundary conditions, and then I believe that with fixed ZM lambda, I'm getting something. Yeah.
so. I think the projective limit would just be the infinite volume limit
Of this with fixed
finite
M lambda.
volume measure.
So you have a lot of points. Yeah. This will be all extremal points. Yeah. Z M
Yeah, I
lambda.
think so.
Yeah. So you have somehow uncountable many extremal. You have big shockers in this, but it's nothing against them.
But I'm
Even so, in this,
skeptical about the ultraviolet
Yeah.
limit.
in this ultra local case, where you forget this term and you take only those, then we indeed we were getting, okay, if you take a sequence, lambda goes to 0, you are getting just, Gaussian measures. If you take, somehow some other combination of m and lambda, you are getting some delta functions in some points, and then for something you might get, something that contains both. Yeah.
So these alternative.
But it's only 2-dimensional.
Yeah, I don't understand, it's a product measure, right? So
It's just product measure, yeah. Oh no, it's really trivial, but it's product measure, but you have to take all possible limits. Yeah, so you are looking on the product measures and the boundaries of them, so to say. At the on one boundary you have delta functions, on the other boundary you have Gaussian measures. Yeah. Because if you take, somehow both of them going to infinity in a particular way, you are getting delta function at some particular value.
Yeah, I mean, it's just like a sequence of variable which you average, because then you have to take the whole.
But it's a bit more optimistic and maybe not quite right, not quite consistent with the picture that the renormalisation group has to say that the continuum limit can be made to look like a linear combination of over these coupling constants of finite dimensional 5/4 measures.
No, this I don't know. I don't know what will be the projective limit. Maybe you will need, somehow different as you are witnessing. Sometimes you have some m will have, some limit that is linear in delta and plus logarithmic term or something like that. And this will be
let me put it this way. So what we actually know that if you took the took a kind of standard notion of compatibility, that a measure, a continuum limit would look like, at a lower scale, it would look like a 5/4 measure with, as you say, a huge number of 5/6, 5/8 and other things added on. So the claim here is that you could replace all of those 5/6, 5/8 and other things added on by just keeping those first three coupling constants at m and lambda, and taking a superposition over the Zm lambdas with respect to some other measure. That's what you're saying, or you could get close to it.
Yeah.
Yeah.
Probably, but it might be that in the limit somehow you will, for example, you will have in this measure of over these parameters you will have some bumps, and these bumps will create different limits. So
I'm less concerned
at the end, the
about
limiting thing will have higher dimension, not only this three. It will have, somehow.
No, I understand there's a lot of possibilities here. It's just that that's quite a strong claim, which that there's an actual measure. I mean, if you're willing to allow signed measures and other things like that to make your linear combinations of Zm measures, then I think you might have a shot at it. But without
this I'm allowing. This I'm allowing because this somehow this is my alpha, and m was defined as finite measures.
Signed measures? I think you have
Well,
to
it's linear space, so if it is linear space, I allow signed measures.
Yeah, you have to allow signed measures.
But I'm somehow, it's finite, and also, somehow probably I have to say that, plus part and minus part is finite, otherwise it doesn't make sense. Yeah. I'm accustomed to use, when I speak about signed measure, always it is, both parts are finite, new plus, new minus are finite. Otherwise I wouldn't know. It's possible to introduce them in more general case, but it's always pain in the neck. So when I was teaching measure theory, I was restricting to signed in this sense. Then the life is simpler.
All right, well.
Okay.
Maybe I should just show you the last slide. And the last slide is, somehow something that I already, in some sense, incorporated. There were some papers that were going in this direction, in some sense. And namely, there was a series of papers by Robert Schrader. And the third one is here, but somehow, there are three papers like that. And what he was doing, he was somehow doing something like what was on this blackboard here, doing somehow looking on the limit, but just this measure new alpha, z, and lambda, and trying to fix this lambda, these three coefficients by somehow fixing some physical parameters. Yeah. Which he was not able to deal with it in any reasonable way, so then he somehow went to to use halfways, he was intermediate renormalization conditions and somehow went. So he started to to use input from perturbative theory, but it started as an idea, okay, let us just fix parameters from the physical world and using them to fix your Bell parameters. For any alpha, lambda alpha, m alpha, and z alpha are defined as those numbers that give you, you know, the physical mass and physical, in this approximation that is giving you physical mass and this thing. But then he was unable to prove anything, so then he started to add this intermediate end. But I didn't study those papers in a very. There are 3 papers like that. You know probably much more about them.